Good afternoon. Welcome to our afternoon session. I'm sorry if that startled anyone. It startled me. We are going to lead off with Raphael Atier, who will speak to us about tracking solar wind evolution with PUNCH flow maps.
Thank you, Sherlyn. Hello, everyone. So yes, I'm Raphael Atier, and I am the co-lead of the working group 1A, in charge of the flow maps for the future PUNCH data. So it's a very exciting moment because it's the accomplishment of a lot of work. So I'll go right into the details of that. Sarah, the keyboard doesn't really respond.
Cameron fixed that for me last time, but I didn't notice what he did.
We just turn it off and on again. Probably. There you go.
Okay. All right. So let me remind you what are the I'll remind you what are the science goals of the working group 1A. Then we'll talk about the solar wind flow maps that the PUNCH SoC will produce. We'll continue with even more advanced tools to create your own flow maps using more advanced algorithms and to access different resolutions of the maps. And finally, we'll go over some scientific overlaps with other working groups. So the working group 1A has 4 science goals. The first one is to measure time-dependent solar wind acceleration from outer corona to inner heliosphere. Second one is to identify the changing boundaries between fast and slow solar wind. The third one is to determine large-scale flow context necessary to relate coronal structure to heliospheric structure. And finally is to characterize the global solar wind conditions through which transient structures propagate. Our sort of prepping work has been using the stereo data. And so we've trained our algorithms a lot on that to really optimize everything. So I'll show you through this data in the absence of PUNCH images. That's for now what I will be presenting the algorithms. So we usually operate with this unwrapped view first. That's to make things much simpler for the tracking algorithms. And I worked on converting the correlation methods from Craig DeForest et al. 2018. At first, made sure that we had a bitwise accurate version in Python, converting from the Perl version of Craig. And this is really this concept and algorithms that will be that are in the SoC and that will be delivering the PUNCH flow maps from the SoC. And so this algorithm has been adapted to a binwise application of the correlation tracking so that we can deliver a more granular flow maps, not just one number of the average speed. The SoC will be delivering, whoops, sorry, I should actually go back. The SoC will be delivering ring averaged flow maps at 4 different radial distances with bins that are 1 solar radii wide over 1,440 latitudinal bins. They will be derived from this intermediate dense flow map that you're seeing now on the screen. And these will not be these intermediary dense flow maps. It's an intermediary data product that the SoC is not delivering to you, but it is what is being used internally to generate the different radial flow maps. So this is an example of these outputs that you can get. You will get straight out of the SoC. There will be 4 different altitudes available. On the last one here, it's a 14 solar radii, but it's because we do not have yet the real data. That third radial profile will be actually much farther away, probably a little bit before the 80 solar radii limit. And so that summarizes really the most basic data product that Working Group 1A is delivering through the SOC. Now, that being said, there is a second method that is called the ball tracking algorithm. Hopefully, most of you have seen me talking about it at different punch meetings in the past. They provide Lagrangian 2D motion vectors of enhanced density structures, not just the periodic ones. They are mesoscale structures, as Nikki wants to prefer to call them now. That algorithm is not officially running within the SOC, but eventually it may happen, but no promises at this point. But the algorithm will be openly available outside of the SOC pipeline to whomever wants to create more advanced flow maps. So I'm going to talk more about this other possibility. So what you're seeing there at the bottom, it's simply a filtered version of the imagery with which the ball tracking work. And so the general idea of that algorithm is to throw balls on these rescaled imagery so that basically the mesoscale structures are seen as little holes. And the balls have an equation of motion that can track and sort of settle down in those balls. And as the flow push them upward, or could also happen downward, but that's more rare, then you get a Lagrangian tracking that's very granular at the feature level. This algorithm has been intensely optimized, and we made sure that we have really the best accuracy possible. One way to check the precision of the algorithm was to having a semi-automated way to identify and track many of different of these mesoscale structures. We selected a broad range of them to make sure that we are not overfitting on a particular type of structure. And the precision that we got was of the order of 1 kilometers per second when doing that Lagrangian tracking. But keep in mind that this is precision, and I want to draw a difference between the words precision and accuracy. Here, that's simply the precision at which we track what we see in terms of optical flows. And so there's a lot of naivety when we do that. The output, again, is a profile similar to what you've seen before, but here I'm only showing the radial profile, but the ball tracking acts in the 2D frame. So we also get the perpendicular motion. I'm just not showing them there because in these particular data sets, the perpendicular motion was 0. At the bottom, you see ball tracking in action. You see all these tags, so these red, these little red crosses. These are the center, they point at the center of the balls that are tracking these mesoscale structures. The numbers that you see, these are labels, and it's by showing the labels that you can see that your tracking is actually working, because you can easily make those plots with those red crosses. It's just threshold and things like that. But the tracking, the quality of the tracking is when you manage to identify in a univocal manner, unequivocal manner, the entire evolution of the structure by giving it a Lagrangian label. So I mentioned there are overlaps with other working groups, and this is an example of a paper from Maher Daye, where I applied the ball tracking to actually track small CMEs. And I apologize, the year is wrong, actually. It's officially published in 2025. So, but Maher is here in the room. I'm sure he can talk more about that after the talk. And so we intend to work with the other working groups that are interested in having the tracking of CMEs. And so you will see you will have this capacity if you use a ball tracking to do that kind of analysis. So I've talked then about two methods so far, correlation-based method and the ball tracking. The correlation-based method is the one delivered by the SOC. The ball tracking is the one that you can run yourself. How do they compare on averages? So I made that comparison. And you can see here, there is some more granular information carried out by ball tracking, and that's the point. when you do the correlation-based tracking, that algorithm loses a lot of the granular information. It smoothes things out. Here you can see there is a little systematic difference between the two. And that is actually well-known characteristics and well-known difference between ball tracking and correlation tracking, which was already sort of solved. And when in the original implementation of those algorithms that were originally designed to track flow fields on the photosphere. And the same kind of systematic differences can be easily corrected. And a very simple way to do that is to simply impose a known drift on the image series and making a fit of that. And luckily, the response of the algorithms to these drifting data series is linear. So you only need to correct by a simple linear multiplication factor. This calibration for the correlation-based tracking will be done within the SOC. You won't have to worry about it, but in the headers information, you will have, of course, information on these calibration aspects if you want to work back from it and make your own calibration. This illustrates how the ball tracking operates on this kind of data, but that's in the case of granulation. And so we have a very good statistics on the tracking of granules. And so this is why those fit work really well, because we have really many data points to do that kind of calibration. And here you can see what happens when we correct the correlation tracking using the same method as ball tracking. And the calibration for ball tracking is done internally. So when you will be using the ball tracking, you will not have to explicitly do that calibration. For the correlation-based tracking, that step is a bit more separate, but it will be also applied. So I mentioned that there's difference between precision and accuracy. Precision is about how well you are able to track the features in a performance perspective and an optical flow. But we are in an optically thin plasma. There are lots of consideration regarding the 3D localization of those features. So the velocity you get needs an extra step of interpretation and approximation to really understand what you're doing. And so this is what I would call the accuracy. And for estimating the accuracy, we have further help from an initiative that has been called the Flow Tracking Challenge, developed by Valmir Moresfilo and Vadim Iritsky. They provide synthetic imagery that have been built upon the statistical properties of the stereo imagery that you've seen before. And they, on top of that, they impose a known velocity profile in the scalar field of brightness to make these structure, the mesoscale structure propagate at a known velocity. And we can use that to determine if we're able to, how well we are able to retrieve the underlying flow field. And so that brings us more closely to actually an estimation of accuracy, not just precision. So to summarize, the SOC will deliver correlation-based radial flows, which are ring-averaged radial speed of the ambient solar wind over at least 4 different radial bins between 5 to 80 solar radii at a 6-hour cadence over 1,440 latitudinal bins. This correlation-based method will be more appropriate for doing large-scale solar wind analysis of acceleration and deceleration over radial distances. If you need more, if the correlation-based method is enough for you regarding granularity, but you just want to have a little bit more of time cadence or a little bit more of radial resolution that is still possible with reasonable precision, and you will have also access to the correlation tracking algorithm, not just the ball tracking. You will also have access to the correlation algorithm. You can run that yourself, derive those dense flow maps that I talked earlier, and derive the profiles at the radii that you want and at the latitudinal bin that you want. Finally, you will have access to these 2D flows made by running yourself the ball tracking algorithm, and that will be available to help you using that to the best of my availability. They will provide you with more granular tracking of heliospheric structure, 2D flows, and ability to forecast CME travel times and trajectories. Thank you.
Yeah, Q&A later.
Our next presentation will be given by Sam Van Kooten of the Southwest Research Institute. His talk is entitled Photometric Starfield Subtraction from Punch Images.
All right. Hi, everyone. I've been around for a while. I've been jealous of Marcus for years, all the stuff that he's doing. And back in November, I became an official member of the SOC, so I'm really excited about that. And I'm just going to take you on a tour of how we're planning to do the starfield subtraction with the Punch L3 images. So the motivation for that is that there are stars in space, and we don't like that. Okay. Let's see. Cool. Stars are beautiful. We all like stars, but Punch is funded under heliophysics, so they gotta go. Not allowed. So here, oh goodness. Where to go?
You. Oh, you're over there.
So here is just the flow chart of how we do it. This is also the outline for my talk. So just to quickly orient you on the full thing, and then we'll dive into all these pieces. We need very accurate pointing information. For each pixel, we need to know the RA det coordinate of that pixel to an accuracy of about maybe 1/10 of a pixel. So we need that level of precision. That item is the only thing on here that's not a slide. I'm just going to assert that Marcus does it. He does it well. The proof will be in the pudding of the L3 files without stars. And that extremely accurate pointing, that will be present in every data product that we provide. Next, we have to regularize the PSF. Marcus talked about that earlier. We need the stars to look the same every time we see them in every image, no matter where that star appears in the image. So we make that PSF very uniform. Then we reproject all the images into an RA DEC frame, kind of making a data cube of right ascension, declination, and image number. We stack all the images up there, and then we reduce the stack to provide one single estimate value for each pixel of what is the constant celestial background at that RA det coordinate. So that's our starfield estimate. We take that back into the frame of any given input image. We have to blur that image just a tad, yes, really, and then we just subtract, and that's the result. So PSF regularization on the right is kind of an exaggerated example of how a PSF might look and how it might vary over an image plane. And Marcus has code that estimates that spatially variable PSF, deconvolves it, and then convolves back in a uniform target PSF. There's more subtlety to that we've discovered. For time, I'm going to keep that a secret, but talk to us if you really like PSFs. So here is that example. Here's an example of reprojecting and stacking those images. So here, these are not Punch images. For this talk, I'm illustrating this method with the Whisper camera on PSP. That's because the code that we're using, I originally wrote it for Whisper. And by using examples from that, I can show you this working on actual data today. Whisper is, I think, a more challenging application for this technique than Punch will be. So at the end of this talk, when you see this working on Whisper, it should work even better for Punch. So here I have 3 sample Whisper images. They've all been reprojected into the same right ascension declination frame. So you can see the field of view is at different positions in those 3 images. And those vertical lines are just marking 3 sample stars that I can see on the screen. I hope you can see on the screen, just showing that they are at the same, XY coordinate in these 3 reprojected stacked images. For the reprojection, we use the adaptive resampling algorithm that Craig put together a while back. It is anti-aliased, it's flux conserving, and so it's a really good choice for this application. So once we have this stack of, it'll be probably thousands of images over a few weeks, maybe a month, that we're going to reproject and stack up. Then we have to reduce that to one estimate value for each RA det coordinate. So here's just a zoom in on a star. So I've marked, a star pixel and a blackness of space pixel. And then for each, you see the distribution of values across a number of Whisper images. For the star, you see kind of a Gaussian spread around some sort of true value for what is the brightness of that star at that RA det coordinate. And then there's a tail of higher values where there's a coronal structure as well, contributing flux along that line of sight. So what I found works well for WSPR was to identify just the inlier pixels there, or the inlier values, fit it with a Gaussian and take the central value. Marcus was finding that for punch, it might work better to do percentile values instead, say just the second percentile of that distribution. And that's something we'll explore as the real data starts to come down. And then on the bottom, you see the empty space pixel. There's a much tighter spread around just a value of 0. So that's kind of how we do that reduction. And then that gives us a star field estimate. So here's kind of an all sky map. It's right ascension going in principle all the way around the sky, but WSPR doesn't cover the entire sky, so I cropped it in. And then vertically, that's declination. Again, I've cropped it in because WSPR, like punch, does not look at the celestial poles. But this is, a cropped down version of an all sky map that has to maintain the full imaging resolution. So it's of order 18,000 by 36,000 pixels. This is a large file. This is a lot of data that we're wrangling on a really beefy server. So you can see the stars. There are a few WSPR specific artifacts in this all sky map. And if you're really eagle-eyed and maybe if you have a little imagination, in the middle of this, there are hints of the Milky Way. It's a little patchy because of some pre-processing I have to do for WSPR. But I just want to point that out to emphasize that this method that we're using, as opposed to something like sigma clipping to remove the stars, this also picks up on faint and diffuse background sources. It's just for every pixel, we're estimating what is the celestial background brightness at that RA deck. So we're going to get the faint stars, we're going to get nebulas, we're going to get the Milky Way, we're going to subtract all of that out. So then once we have that star field estimate, we can reproject it back into the frame of each image that we want to do star field subtraction to. So here you see that, the star field estimate back into this frame. Before we do that subtraction, we need to blur the input image by just a few pixels. That's because so that anti-aliased reprojection algorithm that we use, anti-aliasing means tapering off the high spatial frequencies, and that's just a fancy way of saying blurring the image. So that little bit of blurring is necessary to avoid aliasing. It's of order just a few pixels. So this is actually a GIF that's blinking back and forth between blurred and unblurred, and it should be really hard to tell. It's measured by pixels, not by degrees, and so punch has smaller pixels, so the impact will be even less. Then we do that subtraction, and this is what we get. The stars are, for the most part, just gone. So I'm going to walk you through what you see here. There are some edge effects. A lot of that is WSPR specific. On the inner edge, there's a lot of vignetting, and so the star field estimate becomes a huge over subtraction. And Marcus tells me we're handling that all. There will not be vignetting when we do the punch star field subtraction. There's just a random debris streak. WSPR has a lot of those from kind of the sandblasting of dust and micrometeorites. And I'm just highlighting that to emphasize that like other weird transients don't get affected by the star field subtraction. It's only things that move through the field of view like stars, things that are at fixed celestial coordinates that get subtracted out. There are some detector artifacts. I'm sure punch will be perfect. There are a few bad subtractions. If there's a slight misalignment or a poor estimate for the stellar flux, you're never going to be completely perfect. The bright stars will really emphasize even the smallest fractional error. So that's why you see some problems with the brightest stars. And you expect some sort of residual from just the shot noise. But that's enough of the negatives. Let's just appreciate that 99% of these stars are just poof, they're gone. Like this is really cool to see. This is, I think, really exciting. And this is what we're going to do with punch as well. So this is my last slide. This whole thing is going to be a routine part of the punch L3 pipeline. We're going to estimate these star fields over kind of a rolling window of weeks or months, and then subtract that out of both the clear and the polarized images. Punch will be an easier application than WSPR because the field of view moves through the sky much more slowly, so we get a lot more samples of each star. And we have plans for several ways we can try to remove residuals, those little bits that are left from the brightest stars. We have ideas of how to kind of clean that up as well. And this is the same example Marcus had, just showing this working with punch synthetic data as well. So you see the input on the left, the star field estimate in the middle, and on the right is the star-free kind of blackness of space there. So that's what I have. Thank you.
Thank you, Sam. The third talk of our ambient solar wind session will be given by Steve Cranmer, University of Colorado Boulder. He will talk about mapping the sun's Alphane surface soon with PUNCH.
All right, thank you. So yeah, this is exactly the same title as the talk I gave 2 years ago at the Punch meeting, except for the very soon. So yes, so this is the work of Working Group 1C. I've got Rohit Chiber, the co-lead of Working Group 1C, listed there, and also a current undergrad student, Treston Simon, and past grad student, Gilly, who I think is giving a talk tomorrow. And yeah, we Working Group 1C wants to find the evolving physical properties of the Alphane surface. That's what we want to actually measure with PUNCH. So yeah, this talk will talk a little bit about what that is, how PUNCH will actually detect it, and I'll conclude with a preliminary look at an interesting forward modeling tool that's really helping me to visualize how we're going to do this.
Is there a way to get that the artifact out of there? I think Sam, you did it efficiently.
Let me see if I can do it.
Stop share or whatever it is.
Not a
No,
bad
we
place
don't.
for it.
We do not want to stop share, which I'm sure of.
No, I understand, but that's
That's what it was. Hide floating meeting controls. Oh, there is a command. I'll figure out the control sequence next time.
Great. Okay, so yeah, if you ask different people in solar physics and heliospheric physics, what's the difference between the corona and the solar wind? There are all sorts of either observational or theoretical ideas about the differences between these two regions. A lot of people think it's just one single system that extends very continuously all the way out. But there are some contexts where we do think that there is an interesting way of delineating the boundary between the corona and the solar wind, and that's this idea of the Alphane surface. And I cannot advance the slides now.
it's got to become part of the procedure too.
This has happened a couple times, and the best solution seems to be this.
Cameron just hit something that made it. Can't remember what it was.
Oh, it's your amplitude.
That's what's happening. Oh, for goodness sake.
It's the blue pencil on the side.
Yeah, we need to go to the arrow.
Just press the X down in the bottom corner.
Okay.
Yep, that should be good now.
And now let's see if it'll let us do it. You in the right place?
Yep.
And
Cool.
Forward, yes.
yes.
There's a couple of squiggles, but I think that's because
That's fine. That's
You wanna
let's
see
leave it. All right. Yes. So yeah, the Alphane surface is this idealized place where the solar wind speed first starts to exceed the Alphane speed. Right. This on the right is just an idealized one-dimensional model. The Alphane speed is the speed at which most of these MHD waves propagate radially through the solar wind. It's very high down in the corona because the magnetic field is very strong. The plasma beta is very low. But then the solar wind accelerates and becomes the dominant speed of propagation of features, right? Below the Alphane speed, you can have waves that are propagating both up and down. So information can essentially communicate everywhere in that sub-Alphanic region. But once you exceed the Alphane speed, even the inward propagating waves are being dragged outward by the solar wind. So there's no back communication to the sun anymore. So it's sort of the point of no return for communication of information in the solar wind, sometimes called the heliobase. There's also all sorts of models of the angular momentum evolution of the entire heliosphere, where the Alphane radius or the Alphane surface plays a special role as a sort of a lever arm for angular momentum torquing of the whole system. And also there's an interesting observational trick that since you know that the two speeds are equal of the Alfvén speed and the solar wind speed at the Alfvén surface, if you can measure the solar wind speed there, you measure the Alfvén speed, and you can also measure the magnetic field strength, which is a difficult thing to do in the corona. All right, of course, where is it? We've had decades of 3D simulations and extrapolations from measurements made at 1 AU, and now in the last few years, some actual crossings of the Alfvén surface with Parker Solar Probe. My bold, not so bold prediction, I think, is that PUNCH6 is really ideally suited to be an Alfvén surface measurement tool, because something between 10 and 20 solar radii really is the sweet spot for where we've now started to see the Alfvén surface. This histogram at the lower right shows various estimates of the location of the Alfvén surface from many different measurements. Parker Solar Probe is the one in red, basically from the crossings and from the encounters that don't involve crossings. You can also extrapolate over smaller distances to figure out where the Alfvén surface was. And yeah, those are essentially under the red curve, and there's plenty of other curves from other extrapolation techniques, like from 1 AU, the Omni curve, and all the other curves are simulations. Of course, when I called it the Alfvén radius, that sort of makes you think of a giant sphere. It's really not. You know, that one simulation from Ofer Cohen is on the right and shows it to be this very non-spherical surface. And we think it's even more complicated than that. And in fact, I've got combinations of simulations and measurements from Parker Solar Probe from Sam Badman's Fall AGU poster that shows the first 19 encounters of Solar Probe with the Alfvén surface, and all the green regions that you start to see become more and more prevalent as PSP gets closer and closer are those places that are the sub-Alfvénic regions. So yeah, we've been starting to see it a lot more. There's been a lot of interesting things learned about this region from Parker Solar Probe. Yeah, we've learned about the Alfvén waves and how they evolve radially, and how they sort of depart from some typical expectations of how waves behave in a homogeneous sort of plasma. We've measured things like the alpha particles and found sort of local maxima in some of their interesting non-Maxwellian properties around the Alfvén surface. And also, as we've gotten closer to the sun, the typical periods of MHD waves and fluctuations has gotten shorter and shorter, which that's the one that surprised me the most. 2-minute periods. It's really hard to figure out what's generating something like that. So yeah, it's still a lot of interesting things to learn about this region. But we're here for PUNCH, of course, and PUNCH is an imager, and what we want to see are basically things propagating down towards the sun below the Alfvén surface. That's what's going to tell us that we're below the Alfvén surface. There's been decades of coronagraph and heliospheric imager type measurements of blobs flowing out through the solar wind. It's been much rarer to detect things flowing back down towards the sun, especially up at distances of 10 to 20 solar radii, where we think the Alfvén surface is. The one example that we've thought about a lot is from Craig's 2014 paper. They used stereo core 2 and found several examples of inflow up to about 12 to 15 solar radii propagating down. There's been a lot of theoretical work, scratching of heads, trying to figure out what's up with this data. The cartoon on the right there shows radius versus time. The green curve shows what Craig's extraction of data from Fourier filtering from the Core 2 instrument shows these features essentially slowing down, right? Getting flatter and flatter as it propagates in. That's exactly the opposite of what we expected from linearized MHD waves. You'd expect, because the Alfvén speed is getting bigger as you get closer to the sun, you would have expected it to get steeper and steeper as it goes closer to the sun. So there's been theoretical models abound, and there's been several ideas of what's causing this. There were a few papers by Anna Tenerani and our effort trying to model these things as blobs that are plowing through the corona and snow plowing, essentially gaining mass and slowing down due to that effect. That might be one explanation. The other explanation shown in these sort of 1D randomized plots on the right is essentially that the presence of MHD turbulence might actually produce this slowing down effect. You can see hopefully the red and the green curves on the bottom image, basically showing that once you put in this kind of turbulence, a blob might be going down and then it might be kicked up and down and up and down. And its sort of stochastic motion would effectively slow it down to the types of things that we see. So these are the things that we have to be on guard to be measuring with PUNCH. So of course, PUNCH will give us specifically PUNCH NIFI will give us these nice 4-minute cadence data in this field of view where we think the alphane surface will be. We're going to make the best use we can of the flow tracking products and in combination with this Fourier filtering, so we can hopefully separate out the outgoing and the ingoing features. Possibly with some special information from the polarization as well, if there are dense blobs along the line of sight. Yeah, we are very much indebted to the work of Working Group 1A for the flow tracking algorithms, because we're going to be making very good use of them. Yeah, so there are plenty of questions, and I'm really hoping we can start to answer these questions. Are the decelerating features that Craig saw from stereo, are they just sort of the tip of the iceberg? Are those the densest things? And then maybe we'll see less dense features with PUNCH. Maybe they won't be decelerated as much because they're more small perturbations that are more linear. And I'm also very curious about the lifetimes of these features. That'll say a lot about the evolution of turbulence in the solar wind. The very last thing is a new sort of forward modeling tool that I wanted to talk about. You've already seen a bunch of simulated PUNCH data from 3-dimensional simulations. Those are great for basically giving us a context of, you're starting with 3-dimensional ground truth, you're producing images, and then you can compare with what you actually know is happening in that 3-dimensional volume. And there's a lot of good approaches to that. About 3 or 4 years ago, we started working on a code that we called STRIA that Gilly worked on for his PhD thesis. Sarah helped put it into the forward IDL code. The difference with the self-consistent MHD simulations is that this is sort of more of a building block code where we put in the striations, we put in the blobs, and we know exactly what we're putting in so that when we do the observational synthesis for the polarized PUNCH-like data, we'll know exactly what we expect, and the differences will tell us about how we need to actually analyze those data. So more recently, this sort of code was reinvented in Python with a huge speed up in runtime by undergrad student Treston Simon, and all I'm going to do is just show you a few examples of movies. Here's one just with sort of a 3-dimensional distribution of striations throughout the corona, plus blobs that are propagating both up and sometimes down in sort of a simulated NIFI field of view. The nice thing is we have both the total brightness and the polarized brightness, and the polarization ratio can be plotted as well. Interestingly enough, I'm fascinated by these sort of plus or minus 0.1 swings in the polarization fraction that are going to tell us something about the 3-dimensional structures. The last thing is this sort of simulated J-map, where you take a radial sort of effective slit and then pile them up in time to watch structures propagate in and out. This is one example with structures propagating out and propagating in, again, just using the MHD speeds, going up and down with the speeds of MHD waves as the place to start. But it's interesting to see, what can you see, what can't you see? And yeah, we're going to have to try to understand how to actually re-extract out these the ground truth velocities from things like this. Anyway, that's about all. Yeah, very excited about seeing how real PUNCH data is going to behave, and I think it will improve our understanding of the overall coronal heating and solar wind acceleration. And I always like to end with something that says that all these other instruments and missions are going to be very helpful in giving us more global context, both all the way down to the corona and out into the heliosphere. All right, thanks.
Thank you, Steve. So the fourth talk in our ambient solar wind session will be given by Li-Jun Chen of NASA Goddard Space Flight Center. The title of her talk is The Alphane Surface, a Hole Punched by the April 2023 coronal mass ejection. Can you stop sharing, Risha?
Stop sharing.
Yeah, I'm gonna get rid of the squiggle.
Mm.
Let's this time get it start right from the get-go.
Hey, Jim,
So,
look at your email, please.
and we do.
Hide from me. Yeah, that's right. Maybe. Mhm. That one. right?
Good to go. Thank you, guys.
Hello, everyone. I'm Li-Jun. I am here because Craig talked to me last February about high altitude aurora and the possibility that PUNCH could provide the data to the TRACERS mission. Craig's vision really started me on a journey to learn about PUNCH, high altitude aurora, serve as a little bridge between the two missions, and all the way into this hole in the Alphane surface punched by a CME that turned our planet into a close-in exoplanet. Steve created for us the context of Alphane surface. Typically, the surface is very close to the sun, about within 10 to 20 solar radii. And in this case, this hole is displaced all the way to Earth and embrace Earth inside Alphane surface. What does this do? First of all, this is the picture from our heliophysics missions, MMS and WIND. And you can see in the green box, the Alphane Mach number is below 1 for 2 hours. That 2 hours was long enough to transform our typical windsock-like magnetosphere with a long tail into a magnetosphere with 2 wings connected to the solar corona and no tail, like illustrated here as a close-in. And this is a case just like the moons inside Jupiter's magnetosphere, and will be the case for all the exoplanets that live inside their Alphane surface. So when the solar wind is super-alphanic, our magnetosphere, those field lines will first be blown to the tail. But when it's subalphanic, it just spread out. The wind just spread out. So here's a picture to show the synergy between the 3 missions. MMS at the magneto pause on the day side, and this is a possibility. Tracers observing in the cusp region, looking at, it's a mission with twin spacecraft, observing the consequence of these precipitation. And PUNCH will show us the big, large scale picture of the CME. Craig seeded this question. What will PUNCH see? Now, For this Alpine wind situation, here is a case of high altitude aurora from simulation. So we took that from a global simulation and you take the emission at 2 Earth radii. It's really high altitude. And you can see that most of the emission is on the day side. The white line is noon. So you can see it's mostly on the day side, really. And that's the perfect field of view. I mean, with PUNCH's field of view, it's perfect. You can see it. And now I'm going to move on to soft X-ray picture. And here. So PUNCH will be around here. I mean, 4 of them going around, right? And a terminator. This is a view, if you imagine yourself, put yourself in space and looking at Earth from the dusk. So Y is 30 RE and X and Z 0. So what you're seeing is the beginning, just 20 minutes into that subalphanic interval, the magnetosphere is transforming. 10 minutes later, another 10 minutes later, 40 minutes later. So you can see the large scale topology of our magnetosphere transforming. And just imagine what PUNCH will see. Now, this question of what will PUNCH see is unstoppable. This case is the May 2024 CME, the huge one. And just a case, look at the shock aurora on the day side, again, in PUNCH's field of view. And this is when MMS on the day side, it sees this huge density pulse all the way beyond 100 per cc. And that, with that soft X-ray imaging, that the 2 cuts was almost parallel, and you can see the magnetopause. Now let's look at the movie. This is before the shock arrival. You can see the magnetopause around here, right here. Okay, now we're going to start the movie. Density pulse is coming. There. What will PUNCH see? No matter what PUNCH sees, PUNCH is going to empower humanity to grasp star-planet and star-exoplanet interaction. This is a case when, for these exoplanets, they live within the Alpine zone. But not only that, they're also true for super-alphanic, for those who live outside of the Alpine zone, because you're going to provide us the view of the CMEs and how it really come to a planet and connect to the interaction with our magnetosphere and the magnetosphere of all the planets that are magnetized. Thank you.
Thank you, Jen. Let's see, the next talk will be given remotely by Devojyoti Kanshabanik at the University Corporation for Atmospheric Research. This talk is entitled Remote Sensing of CME Magnetic Field Across the Corona to Heliosphere Using Coordinated Wide Field of View Radio Polarimetric and PUNCH Observations.
Yeah, thank you. Can you hear me properly?
Do you want to speak for a second? We can make sure we can hear you, Devajyoti.
Yeah. Can you hear me properly?
Mhm. Are you there? Can you speak?
Hello,
Oh, yeah.
can you
thanks.
hear me?
Yes, sorry.
Thank
Thank you. Finally got it. Anything else? No,
No,
I think
no.
we've got you all set.
Lynn, do you
Okay.
wanna, it's gonna be,
Should I advance slides for him or will he?
No,
do it?
he's doing his own.
here, you
Okay.
can do it right over here. If you click on this and then do the green button, that'll work too.
Okay, we see you.
Hi, so yeah, I am Devojyoti. Will be presenting, I'll be talking about remote sensing semi-magnetic field using wide field radio observations and why we need the coordination with punch wide light observations. So as we know that we can observe the CME from a very low corona to almost in the heliosphere using wide light. And another wavelength which can provide the which can provide the CME observation is the radio observations. Now, when the CME is at the lower coronal heights, we can directly detect radio emissions from the CME plasma by thermal free emission or guidosynchronous non-thermal guidosynchronous emission. And this can provide actually the magnetic field informations of the CME plasma. But as the CME move away from the sun, these emissions becomes very faint, and also the emission frequency goes below the ionospheric cutoff frequency. But so in the heliospheric regime and inner heliospheric particularly, we cannot detect this radio emission directly from the CME plasma. But what we can use is that the background galactic and extragalactic radio sources. And when this radio emission from this background sources are passing through the CME plasma and heliospheric plasma, their intrinsic properties gets modified by the heliospheric and CME plasma. And if we can measure those changes of these intrinsic properties, we can probe the magnetic field as well as the electron density of the CME plasma. So that's the point that there are two wavelengths across the entire electromagnetic spectrum, that visible white light and the radio. Both of them can be used to observe or probe the CME properties from lower coronal heights also and to the inner heliosphere. Now, we all know that at present, this is a brief overview of what current approach space weather community is taking, is that we have the magnetic field measurements at the photosphere and also at lower coronal heights, and also have the magnetic field measurements by the in situ observations in different spacecraft near L1 point or different vantage point in the space. And in between, we have coronagraphs and heliospheric images observations in white light that provides the geometry and dynamics, but that does not provide directly any observational constant on the magnetic field strength. And these observational gaps are currently filled with the different empirical, analytical, or numerical models. And the radio observations can fill this observational gap of the CME magnetic field measurements in the corona and heliosphere. Although there are several promises the radio community generally make, but there are only recently there are new generation instruments started providing these observations in reality. So, sorry. So the technique that I am going to told you is called the radio heliopolarimetry. It is of using the background radio sources when the linearly polarized back radio emission passes through the magnetized plasma of the CME. The polarization angle rotates, and that we call Faraday rotation. And this rotation is proportional to the wavelength square and the line of sight integration of the electron density and the magnetic field. Now, as you can see in this image on observation taken by Jansky VLA in New Mexico, there are several background sources which are occulted by the CME plasma. And when this emission passes through the CME plasma, their Faraday rotation changes. And if we can measure this Faraday rotation changes and can separate the electron density contribution by the white light observation, we can get a line of sight average magnetic field strength. And these measurements are generally we do in terms of frequency independent quantity that we call the rotation measure. That is the integration over of the electron density and the magnetic field along the line of sight. Now, these observations, these Faraday rotation observations have been done quite for many times for coronal heights up to 10, 15 solar radii. But the question is why we're not doing this for the heliosphere. There are several reasons that we need a wide field of view instruments and send much more sensitive radio polarimetric imagers, because the CME becomes very large in size, and also the contribution of this Faraday rotation by the CME in the heliosphere is much smaller compared to the corona. So what do we need? We need also the low frequency observations, because the Faraday rotation is proportional to the wavelength square. And at the low frequency, we can probe very small changes due to the CME of this Faraday rotation, due to the small changes in the magnetic field and the electron density. And another big challenge is the ionospheric contribution of this Faraday rotation, and the heliospheric contributions are comparable. So we need a very precise separation of the ionospheric contribution from our observation to properly measure this heliospheric Faraday rotation. So what I have shown here is that this left top image shows a typical rotation measure that we expect from a CME as it moves away from the sun. And there are different radio instruments in the world which can provide this sensitivity in the required sensitivity in the of the relative rotation measure. And as you can see, there are some instruments which we can use. Those are mostly the high frequency instruments that we can use to measure the magnetic field below 50 solar radii. But there are other instruments called like MW and LOFAR, which we can also use to measure this rotation measure up to about 100 solar radii and so on. So the main challenge is now the current RM accuracy provided by the ionospheric models about 0.1 radian per meter square, and that generally provided by averaging over a year time scale. If we average an observation over year time scale, that accuracy we can achieve. But for CME observation, we need this accuracy over very small time scale. So for that, we developed a new technique to separate the ionospheric Faraday rotation contribution from the heliospheric from the observation. And what we have achieved is about 4 minutes of observation, achieved about 0.01, about 1 order of magnitude better accuracy in separating the ionospheric contribution from the heliospheric contribution of the Faraday rotation. And this allowed us to detect some fast heliospheric Faraday rotation measurements of the CME using this instrument called Murchison Whitefield Array that is in Western Australia. And this instrument is a very, as the name suggests, a wide field of view instrument, about 30 degrees cross 30 degree field of view, and it's operated at 80 to 300 megahertz. This is an example of what event the CME, which was observed both using the LASCO and the stereo from opposite side of the Earth, and also the stereo heliospheric imagers can observe this. And this figure, the bottom right figure here, shows this orange shaded region is the CME, and the blue shaded region shows the field of view of the MWA during that time. And what we have using this wide field of view instruments, we have simultaneously have about 26 line of sight that is occulted by the CME plasma, so that we can measure this line of sight integrated rotation measure along this 26 line of sight simultaneously. And we used a reference source and for the ionospheric correction. And what we have achieved, we can measure the RM among these 26 background sources. We have detected
Jyoti, can you hear us? We lost your sound. Hold on. Oh, here it comes.
Hello, can you hear me?
Yes, we can hear you now.
Okay, I somehow.
Yeah, sorry we lost you, but if you can reshare your screen.
Yeah. So
There you go.
at what point you lost me? This part?
Yep.
Hello?
Yeah, we hear you. You can go ahead.
Okay, maybe I am stopping my video. That will be better.
Yeah, maybe it's the video that's glitching it.
Yeah.
We
Yeah.
did see, we got as far as you were talking about, we saw where the MWA was in that field of view, for example. Yeah, you'd shown.
Okay. Yeah. So with the MWA, I have detected about measured the 0.13 radian per meter square RM of this around 26 simultaneous line of sight which are occulted by this CME. And this is the first ever measurement of this heliospheric rotation, Faraday rotation by a CME. So why we need the white light observations? Because as you can see, what we are measuring is the rotation measure, that is the integration of the electron density and magnetic field. And somehow we need to separate the electron density contribution. And white light observations can help here to provide the electron density or the electron column density estimations. And having that, we can get an average line of sight magnetic field by dividing the rotation measure and the line of sight column density. So currently, we are limited to one direction in the ecliptic plane due to the only availability of the heliospheric imagers from one of the stereo. And here, the synergy will go because the radio heliopolarimetry, those are mostly those observations are sensitive to the magnetic field strength along the line of sight. But we need to separate the electron density contribution. And the PUNCH white light observation are sensitive to density structures, but not directly to the magnetic field strength. But it will provide a way to separate this density contribution from the Faraday rotation almost 360 around the sun that is currently missing. And this is a fairly new field, and one of the and all these different instruments can provide these heliopolarimetric observations. And these are now we can use these instruments which are distributed all over the world to.
Okay, we just lost you. Pause for a sec. Don't know. WLT, can you hear us? Because we lost you again. Yeah, I think it's just a signal from them because they dropped off. Okay.
Heard from Nikki. Have you-
Nikki's right there. Nikki, why don't you come up? Oh, wait, we hear you again. Here you come.
Okay, I could hear you properly, but somehow, yeah. Okay, I am almost at the end, so just I am finishing.
You're good.
So yeah, so the conclusion is that this is a new way to provide the heliospheric magnetic field estimation, and we need the coordinated observations with the PUNCH white light observations. And we have developed an automated triggering system that can be useful for observe using this ground-based system, and the PUNCH observations and this global heliopolarimetry network will provide a complementary information. So I'm looking forward for this new PUNCH data, and also this heliopolarimetry technique is a very new technique. We have developed almost at a similar, I should say, right time. So with that, I will stop here and thank you.
Thank you. I believe this is the final talk of the session. Yes, so our last speaker will not be joining us, but
Oh, yeah, yeah.
right, but Nikki Weil from the NASA Goddard Space Flight Center, our very own NASA mission leader here, will speak about mesoscale solar wind structures, origins of variability.
Okay. Good to go. Oh,
I think it's a leading scientist.
just making sure that we have, sorry, you're good. Okay.
Can I just hit the arrows?
Try it. Just try it, because that's glitched before. All right. Yep, that looks like it works. Okay, hi, everybody. Oh, I'm so excited to be here and to be hearing all of the wonderful science that we're going to get to do with PUNCH. All right, so I am, in addition to mission scientist, where I help look at the overall big picture and make sure that we actually are going to do the science that we said we were going to do. I'm also in charge of leading PUNCH Working Group 1B. So I'm going to talk about that right now. Working group 1B is to determine how much and what types of mesoscale structure are solar origin, as in created at the sun, as the sun is making the solar wind, versus how many and what types of mesoscale structures in the solar wind are created en route, things like turbulence. Answering this question is crucial for 3 reasons. One, it has strong implications about how the solar wind is formed in the first place. 2, it provides critical insight into where and how that kinetic energy becomes available to drive the turbulent cascade. And 3, this is the ground state of space weather. There are no quiet days in the sun. The sun, because of the way that it makes the solar wind, is constantly having little explosions and making all sorts of structure in the solar wind. And that's what this video is meant to show. Let me see if I can play it again. There we go. This is the Deep Field Core 2. I don't know if it's been shown yet today, but this is a deep field campaign with stereo core 2. And you can just see all sorts of mesoscale structure. The way that the sun makes the corona and solar wind is filled with long striated structures and short chunky structures and periodic structures and all sorts of different kinds of structures. So this is the ground state of space weather, and understanding this and getting it right is important if we really want to understand not just the big space weather events, but the daily driving of the Earth. It's not as big as the big space weather, but it's the constant buffeting. All right. Why do we need PUNCH? Turns out the heliosphere is enormous. And I know we all know this in our heads, but I've started getting in the habit, even in scientific talks, of starting to put scales on things, because even though we know the numbers, I feel like we lose the connection with really why it's so hard to do this. So I've put here the sun. The sun is that purple dot on the left, to scale, with 93 million miles between, and the Earth, which you probably can't even see, but there is a little teeny tiny dot there, all the way on the right, that's the Earth. PUNCH images this whole region, and it sees all the way down to the scales that are needed to understand the impact on the magnetosphere. All right, so just to say that in a different way, we made this little cartoon representation of these mesoscale structures. And the first thing to notice is, again, to say the numbers, which is it's 8 orders of magnitude to get from the scales that we think of as the large scale structures, things like the stream interaction regions and the CMEs, down to kinetic scales. That's 8 orders of magnitude. And what I'm showing here in this cartoon is just an illustration of some different types of phenomena. And the key is that on the largest scales, things like CMEs, things like stream interaction regions, we know those scales come from the sun. Then the kinetic scales, all the those kinetic scales that we see at 1 AU, those all happen because of processes that happen en route, heating, things like that. The mesoscales are this competition between the two. Some of it comes straight from the sun in the same way that a CME came from the sun. Some of it grows newly or is formed between mesoscale structures from processes like turbulence. And so you have this mixture of both going on and actually probably feeding back on each other. And that's what that middle bar is meant to, that middle bar with the pink and blue and the squiggly line. It's just meant to represent that there's both. And then the giant red boxes are meant to point out that both in our observations and in our models, we cannot capture the mesoscales currently. With the stereo heliospheric imagers, you can capture that global scale. You cannot get down even into the mesoscales. With things like Parker Solar Probe, we're really getting right the microscales, but you cannot, again, get out to the mesoscales. PUNCH fills in this gap in a really crucial way and allows us to connect the mesoscales to the global scales. Again, just to probably you've seen this morning, PUNCH does this because we combine our narrow field imager and our wide field imager. And the key is we have this entire field of view simultaneously with the temporal resolution and the spatial resolution. So we can really watch these mesoscale structures, watch them as they advect outwards, watch how they evolve. And because Violet and Oliver always have to make an appearance in one of my talks, This is the kids at the 2017 total solar eclipse. They've got the glasses on because the pictures were taken right before when you still have to wear your safe solar viewing glasses. But if you imagine a total solar eclipse, Punch is going to see not just that corona that you see during the total solar eclipse, but all the way extended down to the horizon, all the way up to directly overhead and fill in that entire space. All right, here I've taken that same Core 2 deep field images, and I've blown up just that upper right corner there. And I've put, again, to scale, the blue dot on that movie is the day side of Earth's magnetosphere to scale. And so now you can just visually see as all of these structures, the long striated one, the short chunky ones, all of them would totally engulf the Earth's magnetosphere, and they do totally engulf the Earth's magnetosphere. We know that they get to 1 AU. We see them in the in situ data. And we know from composition that they're the same ones that left the sun, but we do not yet have the ability to follow them all the way. Punch is going to be able to do that for the first time. And so we're actually going to be able to see these structures all the way to 1 AU. And so you can see why it matters if we're trying to get this ground state of space weather right. And just to put another cartoon up, this is what those look like if you have these density structures, because density is what Punch is looking at. So it's dynamic pressure from the perspective of Earth's magnetosphere. It literally squeezes Earth's magnetosphere. And even on these quiet days, on a quiet day when there weren't big CMEs, still we have many events now where we see that the Earth's radiation belts respond, and not just in an adiabatic way, but actually lead to particle precipitation out of Earth's radiation belt into Earth's atmosphere. And that's what this event here is showing on the cartoon is the left, but the actual data showing wind dynamic pressure and then RVSP data on the bottom. As I said, we know some of these for sure come directly from the sun because of the way the sun makes the solar wind. Here's a set of images where we just literally see this particular kind of mesoscale structure called periodic density structures coming off the helmet streamer. Like I said, from compositional measurements in situ at 1 AU, we know these things survived to Earth's magnetosphere, and we know that they came from the sun. But this is an indirect link. We don't yet have images to be able to follow them all the way. That's what Punch provides. In addition to just the mesoscale structures, I just wanted to also take a step back and point out the sun has magnetic reconnection events, and the sun does it in a lot of different ways. And they're all ways that Punch is going to be able to see the result of. On the far left, I'm showing a paper from Craig and then a follow-on paper from Anna Tenerani showing open nanoflare events that they think are what we're going to see and how we're going to find the Alphane zone. So this is a type of reconnection. This type of reconnection rearranges magnetic field, probably imparts some energy. No mass is released with that type of reconnection. So that's one of the reasons it's hard to see. Jets, jetlets, plumes, those are little reconnection events, but relatively a lot of energy and mass come out with those. And so we'll be able to see probably the evidence of those higher up, because Punch sees over the poles in a way, 5 minutes, okay, that no other imager has been able to see. Of course, the blobs are in the middle there. That's what I was showing. Sometimes they're just random blobs, and sometimes they come out periodically. Stealth CMEs, those kind of like a big blob or a small CME, and there's no flare associated with them. But Punch is going to be able to see those and be able to watch the substructure within them. And then, of course, the classic big flares and CMEs, which other groups will be talking about later. So the sun makes all of these different kinds of events. They're all reconnection, but some of them have a lot of energy and not much mass. Some of them have a lot of mass, but not much energy. And the sun does all of these things, and Punch is going to be able to see the effects of all of these different things in the solar system. Okay, I have 5 minutes. So I'll just say we've looked more in situ now and done a lot of statistics on what those periodic density structures look like. So that's one of the classes of mesoscale structures. And we know that there are two sources. One of them makes longer structures and one of them makes shorter structures. And we have not yet had the imaging capability to really see where they come from. And I think PUNCH is going to be able to help us understand really why we see these two different populations. We think maybe jets and jetlets might be involved with one of them and streamers with the other. So again, because PUNCH's signal to noise ratio, because it has these deep, effectively like these deep field images, but all the time, high resolution, we're going to be able to provide measurements from the large scale structures all the way down to the ground state of space weather. And the thing about the mesoscale structures, my favorite are the ones that come from the sun, but of course, all of those set up shears between them or are the breeding ground for turbulence. And so Yan and Bill and Chucho are talking or showing posters about how the turbulence creates new mesoscale structures on the way. And so then the actual set of structures that hits the magnetosphere is going to be this combination of both things. And PUNCH is going to be able to see the relationship between the two and watch them both develop. All right, so I'll end with PUNCH is going to be able to image the formation and the evolution of the ground state of space weather in a way that no other mission ever has. The end. And we're not doing questions. Oh.
Nope, we're doing it right
Oh.
here. You stay right up
right.
here.
Okay, if I can invite our speakers to come forward for the panel Q&A.
They muted. Yeah.
All right, this is a pretty self-directed process. The microphone is right here. And these folks will have a lavalier. Somebody want to make sure that mic is on? Good. Teresa.
Thank you.
Hello. Ready? Okay.
You could pull it off if you wish.
Someone